to the cloud. Cool, welcome everyone. Hey Maveen, good to see you. And yeah, Mike, so you kick it off when you're ready to go.
All right, ready to rock and roll. All right, so today, today's meetup is Scale and Observability. And we've got some distinguished guests from Grafana Labs, Polar Signals and New Relic, and Pixie Labs, so New Relic / Pixie Labs. Thank you, Josh, for the introduction. I wanted to remind everybody the cloud native at scale community is the frontline for open source cloud computing in the cloud native environment. So these meetups are always informative and educational. So please sign up, please come. Future ones, look at the past ones. It's very, very helpful. I've been so excited to be a part of it. So thank you very much, Josh. So today we're going to talk about observability, obviously, and with the vast and rapid adoption of cloud native technologies at companies both large and small across the industry, and the increased velocity of execution and innovation, rapid change, scale observability is paramount to that success. Knowing what your systems are doing when they're not doing what they're supposed to be doing, and proactively knowing where you can optimize is critical to business success. And we have a very distinguished set of cloud native practitioners here today. We are very, very excited to introduce. So I will quickly go through that after I tell you a little bit about swag, because everybody loves swag. Acuity is the sponsor of this meetup today, and it's a young Argo-based company with the aim of delivering Argo CD as a managed offering in the cloud soon, and also serves as an enterprise company for those that want to leverage any of the Argo projects and any of the Argo adopters out there. And they're happy to be part of this meetup as a sponsor, and very, very excited about all the cloud native technologists that are here. And they have a swag raffle. There's a landing page, Josh. I'm not sure if that's quite ready yet, but I'm sure it'll be part of the postmortem or part of the actual
I'm dropping it right now. So hopefully we don't crash the website. Ha ha ha. Let's see here. Boom.
All right.
So every third sign up on the newsletter gets some swag.
Indeed. All right. So that's every third sign up on the newsletter gets some Acuity swag, and their logo is awesome. So you definitely want this swag. All right, so we are going to go in order of introduction. I'm going to introduce Natalie first. Natalie Serrino is a principal engineer at New Relic and the founding engineer of Pixie. She focuses on the open source Pixie's data layer, more specifically the PXL language, the compiler, and the edge query engine for analytics. After that, we will go to Frederic Branczyk, CEO and founder of Polar Signals. Before Polar Signals, he was a senior principal engineer and the main architect of all things observability at Red Hat. I love that line, by the way. He joined through the CoreOS acquisition, and Frederic is a Prometheus and Thanos maintainer, as well as a tech lead for special interest group on instrumentation in Kubernetes. And finally, last but certainly not least, actually not last or least, Joe Elliot, principal engineer at Grafana Labs. Been working as an SRE DevOps infrastructure person for Kubernetes for the past 4 years. He's the creator of Tempo, way to go, awesome, a Jaeger maintainer, and has contributed to Open Telemetry, Collector Loki, Cortex, and probably many other projects he did not list on his socials. So open source for the win. Thank you so much, Joe, Frederic, and Natalie. I also want to quickly introduce a amazing cloud native engineer at BlackRock, Ryan Olmstead, who's going to participate in the panel discussion towards the end of this meetup. And with that, Natalie, take it away.
Okay, great. Thank you. I'm just going to share my screen. And this will be kind of like a combination short presentation and demo. So let's get started. Okay, is this visible?
Yes.
Okay, great. Okay, cool. So yeah, as said, I'm an engineer working on the Pixie open source project, and I'll tell you a little bit more about that as we go on. And, I am kind of coming into observability from the data space. And so, when you have a hammer, everything looks like a nail, of course. So I'm just going to say that observability is a data problem. So let's dive into, why we can say that that might be the case. So when we're thinking about observability and, practicing observability, in our jobs, we think about certain categories of tasks that, also come from the data space. We want to visualize the data that we have to understand what's happening. We want to get insights from the data. We want to do anomaly detection, maybe even use some machine learning. And we can say that this is kind of the ML and analytics bucket of observability. And this is very well supported by the organization. So if you take this picture here, and that's the organization, we can say the ML and analytics bucket is this child right here. So organization loves this stuff, in my experience at least. You have this next bucket of work that applies to both observability and data, which is you have to figure out what to measure. What tools are you going to use? What vendors are you going to work with? What open source projects can you leverage? This doesn't get quite as much attention, but it's still a very important part of the work. As you might predict, there's a final bucket here, which is kind of the glue work, actually collecting the data that we need. You hear about the 3 pillars of observability with the logs, metrics, and traces. I would also put events in that category because they don't have to necessarily be those things. Piping the data from one place to the other can take a surprising amount of the time. Data cleaning, schematization, pre-processing, this stuff ends up sucking up most of our time. And I would say that it gets to this corresponding spot in our tortured metaphor. So if observability is a data problem, it actually, like any data problem, gets a lot harder at scale. You have problems with the performance of telemetry agents. They need to scale efficiently under production level throughput and workloads in order to be useful to you. But resource utilization is actually highest at the worst times. I think we've all experienced when you have a spike in traffic and then your agent's using 80% CPU or something like that, and you can't even see what's going on because it might even take down your application. Efficiently storing and querying huge data sets is a major challenge because when we're talking about machine generated data, that can produce a lot of data that you need to look at in order to understand what's happening. You can start thinking about long-term retention. You can start thinking about, do we need to sample this data because it's just too dang big? High cardinality sources. If you want to give anyone a high blood pressure spike, just talk about high cardinality data and see what they say. Also, this is more of a people problem, but supporting the needs of dozens of engineering teams. If you're at a large enough company, you have to have your observability solution work across teams that may have different practices, different stacks, et cetera. And this can be a major challenge to, making it happen. So we can't talk about all this today. So I'm going to focus on a part that I think gets the short end of the stick sometimes, and that's collecting the right data in the first place. Collecting the right data, which I found in the data space, in research, and also in observability, is oftentimes half the battle of what we're trying to do. It can feel like fighting Hydra. As soon as you cut off one head of the beast, another one grows to take its place. It feels like it's impossible to get full coverage of what's happening. Even once you get that, like we said in the last slide, agent performance is usually the next can of worms. We get CPU spikes, we get kills. It can just be rough. If you get complete visibility, it can be a big performance issue. So a group of us decided to build the tool that we always needed to make it easier to collect this data. And that's the story of the Pixie open source project. So Pixie is a cloud native sandbox project. And basically, there's a lot of cool things about Pixie, but the thing that we're going to focus on is the fact that we collect the telemetry information using Evpf. And this gives us both a performant and low people overhead way of tapping into the rich machine data sets that you need to be doing your observability work. So we're going to quickly deploy Pixie, and then I'm going to tell you a little bit more about Evpf, because I think it's the kind of thing that a lot of people talk about. It gets a lot of hype, but what is it? What is it actually about? So I have a Kubernetes cluster. Okay, kubectl. running some applications. I've already installed the Pixie CLI. So this is an uninstrumented cluster. I'm going to run px deploy. This is Pixie's way of installing all the eBPF probes on the cluster.
So hold on. So somebody's saying, can we see the screen?
Oh, is it not visible? Is it only sharing? Oh, I see. I think I might be only sharing a window. Hang on. Can you see my terminal?
No, we
No.
can
Oh,
see.
okay.
Yeah, it's just your presentation there.
Okay. Sorry. Let me.
Thank you, PK.
Yeah. Thank you for surfacing that. Is it visible now?
Yes. Yeah.
Okay. So basically, px deploy my Kubernetes cluster. I'm deploying Pixie on there. Pixie is going to install a bunch of eBPF probes to start taking the telemetry data that we're interested in. And it'll take just a couple minutes. So while it installs, I'm going to go back to the presentation and tell you more about eBPF. So I didn't have to manually change my code. I didn't have to do anything. I just had to run that one command line and it'll do all the work for me. So Pixie uses eBPF to collect rich data sources. And this really shows the power of eBPF for observability and why we think that it's going to be the solution that people have for the problem of collecting the right data in observability. We can collect the table stakes stuff like process stats, CPU, memory, other resource statistics, network statistics, like who's talking to who. The funny thing about that is we often get people who say, these two things shouldn't be talking to each other. I think your data is wrong. And then when they dig into it, it turns out those two things are actually talking to each other. Protocol tracing, so we can capture full body application requests, DNS, Kafka, SQL, etc. And I just want to emphasize again that this is an open source project. So we would like, any contributions, anyone in the community. This is not, this is 100% CNCF. We can do CPU profiling, and Frederic will also talk about, I presume, talk about some of the great CPU profiling that they do with Parka. We can run BPF trace scripts in order to collect custom data sources if Pixie doesn't have the thing that you're interested in right away, and also dynamic logging. And the great thing about eBPF for this use case is that it means no code changes, no redeployments, and less than 5% CPU overhead. But how does eBPF actually work? What is it? The way that you can think about eBPF is that it's like a breakpoint in a debugger. I have this send pong function, maybe, and I want to interrupt execution when that send pong function happens, just like in any other debugger. But the difference is that instead of stopping the program until the programmer can interact with it, what eBPF does is it stops the program, runs whatever hook you've registered for that breakpoint, and then immediately resumes execution. And because eBPF works very deep in the Linux kernel, it's very efficient and very fast. So it's an efficient way to do this instrumentation. So if I instrumented this send pong function, I might have eBPF code that counts the number of times this pong function was called. So this is the hook that gets called, and then this is the application code that's running that triggers it. But one important thing that a lot of people wonder about at this point is, can you just do anything eBPF? Isn't this like super dangerous if you can instrument arbitrary syscalls, arbitrary parts of the application? Like, isn't this like really hazardous? Like, why would the Linux people do this? Well, they thought about these problems. They don't want your eBPF code to crash an application or slow it down or create any issues. So there's this really cool thing called the Evpf Verifier. And this is worth its own talk. But the high level thing about this verifier is that it only allows you to do a very, very specific set of tasks when you're actually doing an eBPF hook. So it will actually reject things that use for loops or things like that because it can't know when they're going to terminate, or it might be introducing something bad into the code. So this is there to guarantee the performance and the stability of the whole system. So let's just take an example for tracing network traffic. What we can do with, and this is what we do in Pixie, what anyone can do with eBPF is I have my Kubernetes application and I have put probes, or Pixie has put probes onto networking related syscalls, connect, send, receive, close. And when those syscalls occur, our probes get fired and they collect the information that is passed into those syscalls. And this allows us to get the information about the request, what's happening, what IP did it come from, and things like that. This then is forwarded to the agent, essentially, Pixie's agent, to store and parse. Then you can query it and analyze the data. But you might be wondering, what about encrypted data? Turns out there's an eBPF-based solution for that as well. You can actually trace the SSL libraries. This will allow you to see full body application requests, even if they're encrypted. And this is really helpful because these days, honestly, everything should be on SSL. So, okay, Pixie's been deployed. Let's go check it out and see what we can get with it. And yell at me if I need to stop.
You have plenty of time.
Deployed. Okay, great. So I'll be brief, but right off the bat, we can see that there's a visualization of the service map of all these services that are talking to each other in my cluster. And this is something that I just got by default after deploying. I can see the various namespaces that I have, the nodes that I have, some information about their CPU usage, the number of pods. So let's go into my sock shop application. So this is some information about my sock shop application. I have various services. You know, maybe the latency on this front end service is problematic and I might want to dig into that. I can also go into an individual pod and see what it's doing. I can see its HTTP requests. I can see the latency. I can see CPU and, you know, other kind of like merging application and resource statistics together in one spot, because sometimes that information can be kind of siloed. And then what we can also see is like a profile of like where the time is being spent. And this can be useful for us when we're actually debugging Pixie itself. Like, why did it get slow all of a sudden? We can actually use this flame graph. And I'm going to show you one more thing. Which is the raw data. I mean, I always like to drill down into the raw events that happen. I get frustrated sometimes when I see like an overly summarized view of something. So you can always go look at the raw events for what happened. Like these are the response headers, these is the response body, etc. And all this stuff is, you know, written by a script. And so you can just write whatever script you want to do analysis that you care about. Okay. There's a lot more I could show you, but you know, we have two other great presenters coming. So,
We do, and
oh, pardon?
I was just going to say that you're ahead of schedule, a minute
Oh, I
ahead.
am.
So
Okay.
we do
Well,
have a question.
Okay, let's hear it.
and Bravo, by the way, very slick UI and very demo gods are with you today. Look very good. Thank you so much. Can we get distributed traces in Pixie?
Yeah, so that is an important thing that we're working on that doesn't currently exist today. Today we have spans, but the thing is that we're working on open telemetry import as well as export. So, you know, if you have it instrumented somewhere else, you can import it into Pixie, but it is something that we're interested in adding. And so, you know, stay tuned, basically.
Awesome. All right, there's no other questions in, so we will immediately segue to Frederic. Frederic, the stage is yours.
All right, let me share my
Thank you so much,
screen.
Natalie.
Yeah, Mike, maybe just announce towards the end, we'll have a panel and Q&A, which I just announced.
Thank you for doing so.
Sure.
Yeah, so Frederic, while you're revving up, as Josh just mentioned, we will have a panel discussion at the end. So any questions you don't get in now for Natalie, by all means, continue to funnel them in. We'll get to them at the panel discussion at the end.
Yeah, and PK, I know you had a question there, so we haven't, we saw it and haven't forgotten about you. So go ahead and drop it.
All right, Frederic, all yours.
Oh, his audio. Can't hear you.
It's odd. So for some reason, Zoom mutes me the moment I share my screen.
We got you.
One more time.
Natalie, that was a great lightning presentation. I really enjoyed that.
Yeah, I think they say like 1 minute per slide, but I talk fast, so I guess that condensed it a little.
Sure.
All right, we'll try it this way then. Whoops. Can you see my screen?
Yes.
Yes.
Okay, awesome. Then we'll just do it this way. All right, awesome. So yeah, first of all, thank you, Natalie, for that awesome presentation. And there were already a couple of kind of hints at what I'm going to talk about. But essentially, the way we wanted to kind of set up the conversation was kind of Natalie talking about these like data sources and how eBPF is kind of creating ever more data. And now I'm kind of going to take the conversation and continue that, but also transform it a little bit in terms of something that Natalie also kind of touched on, which is the difficulties of scaling storage of these systems. So we're kind of talking about like all of this new data that now exists with eBPF and that we can collect at low overhead. How are we even going to be able to store it efficiently and like query it efficiently? And so we're going to look at one more data source in a little bit more detail. Again, Natalie already touched a little bit on it, but I think it deserves, because it's my full-time job, deserves a deeper look and how we're kind of solving the scalability issues with this. So without further ado, I want to talk a little bit about continuous profiling. So continuous profiling, probably everybody is already aware of profiling, and profiling has kind of existed ever since software engineering has existed. When I like founded Polar Signals, the company that kind of that I founded that does primarily continuous profiling, we kind of did the research and we found that really since the like 60s and 70s, profiling tools have existed. And basically it's natural because we've always needed to understand where resources are being spent by our software. And profiling often has this connotation though, kind of two problems it has. One, you never have the profiling data that you need. And two, it kind of has this connotation of being high in overhead. And again, Natalie already showed a little bit about how this can be solved, but I want to dig a little bit more into the methodology here. But more on a higher level, continuous profiling was kind of first described by Google in a white paper that they called Google White Profiling, where Google kind of explained how they're profiling absolutely everything in all their data centers all the time, and how that essentially solves this problem of not having the data when you need it most. And of course, it's kind of easy to say, well, I'll just always collect all of the data, and we'll get to how that is possible. But when you have this data, there's a whole lot of super interesting analysis that we can do with it. In particular, because we have data over time as opposed to just a point in time now. And if we look at continuous profiling, it's kind of in the sense, just like the word says, we just always profile. So every 10 seconds we take a profile and we store the data that is taken within that profile, and we do that at relatively low frequency. So we only look at relatively few amount of data. And just to illustrate that, I want to show a couple of kind of actual data points from the Parka open source project here. So we've got this metrics graph at the top, and we can select a single profile in time. And as we can see, they're relatively uninteresting by themselves. So each of them have relatively few samples in them. And maybe there's a particularly high spike. Maybe then it's interesting to see the individual profile. But what I wanted to illustrate is what actually the kind of power of continuous profiling is. And that is when we don't only look at a single profile in time, but actually merge all of this data that we're now collecting throughout time as opposed to a point in time. And it can therefore create kind of a statistically significant representation of our process and where CPU time is actually being spent, not just at a point in time, but actually representative of the entire lifetime of our process. And this is much more useful in terms of, I want to reduce the overall CPU usage of my program as opposed to a point in time. With a point in time, we don't really know whether this is representative of the rest of the process's lifetime. And so when we then take all of this data across time, now we get something that we know more to look like more of a profile that we've taken at a very high frequency where we get very dense data. But the point is now it's actually statistically significant throughout time and not just a point in time. And so there are a couple of strategies that we need to apply to be able to make this work in production. And the most important one here is that we do sampling profiling. There are kind of two main areas of profilers. There are like tracing profilers that actually trace absolutely everything that happens in our process. It's almost like a debugger. And those are super high in overhead because you actually need to record absolutely everything. But in contrast, sampling profilers only look at the current stack trace at a controlled frequency. And actually, it's a little bit more complicated than that. But essentially, the way that we can think about it is that at most, we're looking at stack traces 100 times per second. And so using sampling profiling, we're actually able to get really low overhead. And because we can control the sampling rate, the lower the sampling rate, the lower the overhead. But because we're still profiling throughout all of time, over time, the profiling data gets more and more statistically significant. And so even though we're doing this at low overhead, we still get super useful and high quality data. And the last trick, and this is kind of what Natalie also alluded to, the last way that we kind of squeeze even more performance and less overhead of collecting this data out is by utilizing eBPF for kind of all the great reasons that Natalie already explained. So I won't go into too much detail about it, but roughly the way that we can think about it is that the eBPF program, just like Natalie said, it runs in kernel space. And so it's super efficient in terms of being able to grab the current stack trace, because that's literally how the operating system executes our machine code. And so for 10 seconds, we just don't do anything. And we let our eBPF program populate BPF maps. That's how you kind of share data from an eBPF program with our user space agent. And only every 10 seconds do we grab all of this data that, by the way, is also already in the right format and exactly the data that we need, as opposed to, off-the-shelf profilers that may be doing way more things than we need, and therefore create much more overhead and kind of unnecessary conversions that we may not need. And so kind of all of this combined is why continuous profiling is actually possible at low overhead in production. But again, and this is kind of where Natalie also mentioned, this can become a problem, right? We're talking about a lot of data. And if we're just doing a calculation here for a single process per day, a single process per day produces over or almost 1 billion samples. So if we think about the amount of processes across our machines with hundreds of hosts, that can mean tens or hundreds of billions of samples per day that we're looking at. And so these become incredibly difficult to store and query. And specifically, storage is something that I wanted to dig into a little bit more. And when we kind of started thinking about this problem, we kind of just thought to ourselves, how did other projects solve some of these scalability challenges, right? And it was already mentioned in my intro, but I happen to also be a Prometheus and Thanos maintainer. And so kind of naturally, these are two super popular projects. If you're not familiar, Prometheus is kind of the like de facto standard monitoring system in the Kubernetes ecosystem, and Thanos is kind of a scale out solution for Prometheus. So Prometheus was very intentionally created to be only a single process, a single binary, super simple, and it would only scale as large as you can make your machine. And that was very intentionally done. And there's nothing wrong with that, but the reality is that we can't just ever increase the size of our machines. So in really huge environments, it is absolutely necessary to have a solution that can scale horizontally. And so this is kind of where the Thanos project came in. And there were other projects around this time as well, when kind of the inception of the Thanos project happened. But I think the Thanos project is particularly interesting to look at. And I'm not saying this because I'm part of the project, because I had nothing to do with when these architecture decisions were being made. I only came in afterwards. But I think, and because we can see this across kind of a lot of other projects, I think there's one really key element to, in terms of the architecture, that a decision that the Thanos project made that has made it particularly successful. And that is that the entire architecture of Thanos, and I don't know if you can see it, but what I circled here is object storage. And kind of basing the entire architecture around object storage sets up for a couple of really interesting characteristics. And that I wanted to dive in a little bit more. If you're not familiar with object storage, essentially, it's kind of something that most cloud providers offer. For example, on Amazon, it's Amazon AWS S3, or on Google Clouds is GCS, Google Cloud Storage. I forget what they're called in other clouds, but basically every major cloud has one of these, or there are also various solutions that you can self-host. But as opposed to having a local file system, you have an API where all you do is you request a key and you get kind of a blob of bytes back. And the kind of interesting characteristics that we can sort of assume about object storage is that we can assume that it's pretty much infinite, and it's a single central storage. And the interactions with an object storage are relatively simple. I already said everything's kind of based on interactions based on a key, and you get some byte blob. And so the interactions that you can do is you can write a key, you can get a key, you can delete a key. And there are a couple of special things that you can do, which you can get metadata, a full object, and even just kind of parts of an object. And using these, the Thanos project was essentially able to build its entire database, and the entire kind of file layout was built so that it could work really well with object storage. Excuse me. And so because of the kind of fundamental things that we can assume about object storage, that it's effectively infinite, and that it's central, meaning we don't have to think about things like, where are my disks? Are my disks large enough? Do I need to resize them? All of these things we don't need to worry about with object storage. And we also don't need to worry about how to access it. Where in my cluster is this data? There's just a single place that we can access it. And so this is way easier than having to deal with kind of distributed file systems that, you know, use outdated APIs like POSIX. And so my hypothesis that I kind of went into here is that I feel like the Thanos project kind of started a revolution. And while Thanos wasn't the only project that was kind of doing a scale out Prometheus solution, I think it did inspire many of the other observability projects out there. And we're going to hear from Joe in a little bit. But kind of after the Thanos project introduced this, another scale out Prometheus solution called Cortex also kind of is actually reusing parts of the Thanos storage. But similar thing happened with Grafana Loki and with Grafana Tempo. And so I think that basing your storage around object storage is a really sound decision for observability because of all of the things that I've mentioned. And so this is essentially exactly why we at Polar Signals, for continuous profiling, we're building a columnar database that is backed by object storage. It's something that's still very much work in progress, but it's something we're super excited about. And this is all kind of in the open and done as part of the Parka open source project, our continuous profiling open source project. But yeah, even when we do work with object storage, there are scaling difficulties. And that's essentially where I'm gonna kind of stop here and hand the mic to Joe. But thank you so much for listening. And as I said, if you're interested in any of this, you can head over to parka.dev. There you'll find everything about the continuous profiling open source project. And it's kind of, yeah, the columnar store work is still very much work in progress, but within the next couple of weeks, there's going to be a lot of movement around this. Thank you.
Awesome. Frederic, thank you so much. Very comprehensive. You are very much on time, so thank you so much for that. I wanted to pause before we head to Joe and just remind everybody that Acuity is sponsoring this. I feel like I need like a really deep DJ voice to do this, but I'm not going to use it. But you know, again, Acuity is a young Argo-facing and focused company. They aim to have a hosted solution for Argo CD, but they also help people with any relevant Argo project. They are sponsoring this. They have a swag raffle, so every third person that signs up for the Argo newsletter off of the landing page that Josh shared will get a Acuity swag bag. And with that, we're going to go back to the presentation. Joe, the stage is yours.
Howdy. I'd like to thank Natalie and Frederic for kind of setting me up here. Definitely a lot of what Natalie talked about in terms of new sources of data, new ways to collect data, like lowering friction for creating data. Of course, is going to make way more data, and we always want to keep it around as much as possible. Frederic did a great job of talking about continuous profiling and then kind of setting up object storage as an option to store this data in. So what I'm going to talk about is some of the practical applications or some of the practical problems we've had storing, you know, massive amounts of data in object store, requesting data back, and maybe we can learn a little bit about what it is like to interact with object store through Tempo, our distributed tracing product. So let's see here. I should be able to present. Can you all see this thing here?
Yep.
Okay, cool. So let's talk about object storage. We're talking about how we use it in Tempo. And I imagine Thanos and Cortex and a lot of these other projects have similar issues, but we're going to kind of deep dive this from the perspective of Tempo and some of the choices we have made. So real quick, what is Tempo? Just want to set this up a little bit. Tempo is a distributed tracing backend. And we use it. It's Grafana's open source distributed tracing backend. Right here's a Loki query, and so this is just going to track our request as it passes through our system across a lot of different microservices. And Natalie showed us some awesome ways to collect this data. And I know that they're also working with open telemetry to improve the ability to build these traces and to get these into a backend like Tempo. So at Grafana, we were actually using Jaeger for a long time. And we were kind of consuming about 15 to 20,000 spans per second. And we wanted to build something new. And the thing we wanted to build new was distributed tracing built on object storage. The reason being how expensive block storage can be. So we had Jaeger, and it was backed by a Scylla cluster, which is a Cassandra compatible database. And this database was just 90% of our costs of running Jaeger, basically, the memory, the CPU, as well as the block storage to hold all of this. So we were kind of moving in the direction of object storage for a lot of the reasons that Frederic kind of highlighted there. We also, at first we built just like a trace by ID store. We did discoverability through our logs and exemplars. That's changing now. And then we wanted compatibility with all of the major open source protocols. So we have this goal basically to go from 15,000 spans a second to multiple orders of magnitude above that, as while keeping costs low, having way more data to analyze, and have a lot better coverage of our requests. Natalie talked about sampling very briefly. Sampling is a big part of distributed tracing because of the sheer amount of data it generates. And one of the goals of Tempo is to downsample as little as possible, possibly none, because you're saving so much money by putting things in object storage. So why? Why object storage? This is kind of the easiest way to show the answer, which is the cost of all of the different major kinds of storage, well, at least some of the major kinds of storage here. So this is a cost per month, and I just use kind of Google Cloud's pricing. I would guess AWS is roughly in similar kind of universe, and Azure, sure, probably, I'm not sure. But we're looking at order of magnitude difference from keeping things in memory, keeping things on block storage. So block storage is like mounting an SSD or mounting a disk.
Hey, Joe, your audio just went somewhat quiet. We can hear you, but barely.
Okay, yeah, Zoom really likes to read. Okay. A little bit better?
Yes, you're good.
Thank you, sorry. Zoom loves to readjust my volume. It's maddening. I'm gonna try to keep this up here for y'all. Please interrupt and yell at me again if that happens.
Will do, thank you.
For object storage, we have the cost of memory, the cost of block storage, and the cost of object storage are an order of magnitude difference. So when we built Tempo, we made a choice about what are we going to keep in memory, what needs to be available at that kind of speed, and what can we put on block storage, how much we're going to put in object storage. And you're kind of making choices about your tiers, how much data, how much retention do you want in each tier, and how much are you willing to pay while you do this. And here's kind of the trade-off, the amount of time it takes to read that data back, right? So these numbers, the first two numbers come from a very common, you've probably all seen this, it's like numbers every programmer should know, or numbers every engineer should know, and they talk about the latencies of accessing data at different levels, like in cache or L1 cache or in a register, basically. And so object storage is way slower than what is in memory, or certainly what's on block storage. So if you can tolerate this, so like we're looking at 250 milliseconds, if you can tolerate this latency, then you can suddenly build a database or a solution that gets that advantage of having the much cheaper pricing. So here's some Tempo stats that show like how much we're storing, as well as how long it takes us to get back this data. So we roughly ingest about 230 megasecond. We're a little down from our peak, which I think was around 400 megasecond. 1.5 million spans per second now. So remember with Jaeger, we're in like 15 to 20,000 range. So we're several orders of magnitude above that. And in our object storage, we have 94 terabytes of compressed data, of compressed trace data. And this is about 3 billion traces. And latency is an important question here, right? If you can see in our graph here, hopefully that's kind of readable, but you can see that the P50 is down here about 250 milliseconds. The P90 is, I don't know, maybe 500 milliseconds, sometimes spiking to 1 second. And you can see the P99 going up into the multiple seconds, single digit seconds. our database can easily tolerate this. I think for expectations of requesting a trace from a backend of 3 billion traces, I feel like we're hitting good latencies. Whereas if I were setting up a Redis cluster or a Memcached cluster and I was getting these kind of latencies, I would immediately go try to figure out what's wrong with this. Those key value stores have expectations of returning data much faster. They keep data in memory, they keep data on block storage. So when you're making a design decision about using object storage, you're of course also making a decision about, what's the performance characteristics of the database you're trying to create. And I think tempo and a lot of observability data can hit these low single digit seconds on P99 and be very powerful databases that do exactly what we need, that give us data in the responsive ways we want. So I am kind of in Frederic's camp here, where object storage is a great opportunity for observability data, which we collect so much of. So real quick pricing breakdown. So with object storage, it's about 30% of our total cost. By the way, everyone at Grafana hates pie graphs, which is why I wanted to include one. But our object storage is about 30%. And it's roughly about the same as the amount of CPU we use. And then memory is a little bit less. And we can see we actually do have some block storage. We have kind of a wall mechanism when we ingest data. We batch it up on disk before we ship it off to object storage. And then also I have this other category. In fact, I should have just renamed that. But the other category is the cost of accessing object storage. So one of the drawbacks of using object storage is every single request, a GET or a PUT, costs some amount of money. So it kind of needs to be part of your calculation when you're making these kind of choices. With block storage, this is what the pie graph would look like. We're starting to be dominated by our storage costs. And then for fun, I went ahead and graphed out what it would look like if we went ahead and just tried to keep this all in memory, which would be an insane amount of memory, but why not? And it's at this point, there's just no point in building this. It'd be very fast, but you would not want to pay this amount of money to store your traces, I guarantee it. Okay, so the good parts of using object storage. Why? We talked a little bit before about why, but let's talk about some of the other goods. These are GCS kind of numbers here, but 9s everywhere, right? AWS is going to quote you a stupid amount of 9s for durability and availability, as is GCS. Azure Blob Storage does too. And so you have this like confidence in the thing you're using, or the kind of the backend you're using. We'll actually look at why those 9s are kind of deceptive in a second. Mature tooling. Also, like S3 and these things have awesome tools, like in terms of mirroring, so you can have multi-region backups if you need that, or if a customer needs that. Versioning is amazing tools, all kinds of CLI tools, well-documented APIs, existing clients in every single language you can think of. S3 has even kind of become a standard. MinIO supports it, Rook supports it, lots and lots of other things support it. So if you write code to use S3 APIs, you're kind of opening up a whole stack of object storage options, not just S3. It's highly available and operationally simple, almost doesn't count. Like it's beyond simple to set up a simple bucket and some permissions to allow a application to access it, compared to building and maintaining Elastic cluster or building and maintaining a Cassandra cluster. They're not even the same universe of operational complexity. So what's different about it? It can't be that easy, right? So failures are common. Like requesting data is going to fail a lot. In fact, it happens all the time. Not like with block storage, failures are rare. Maybe you have a couple replicas, and if one of your disks fails, whatever, replace it. Do some kind of strategy to recopy the data that's supposed to be on that shard over it, and you're done. Failures are uncommon with SSDs. Failures are constant with object storage. Also, when you do these kind of massive search queries where you're accessing object storage in parallel, because that's the only way to get a trace out of 3 or however many billion I said earlier, or in any kind of reasonable time, this all has to happen in parallel. You're going to be always punished by the long tail. Your long tail is always going to get you. And you're paying for the requests you're doing to this object storage, which is different, of course, than block storage. You also have to be a little more careful at your data organization because of the data they're accessing, the way you're accessing it. It will, you have to think about it differently when you use object storage, partly because of that simpler API that Frederic talked about. Also, a database that's or uses block storage will often read very small amounts of data very quickly and rely on the operating system to buffer this data. And these like characteristics don't exist in object storage. If you want to access, a couple bytes here and a couple bytes here and a couple bytes there, you've already made a poor choice, I think, in object storage. You want to access big blocks of data at once. So we're going to talk a little bit about our data organization, choices we made there, as well as what data access looks like. So failed reads. Reads always are failing in Tempo. We have one cluster internally. It's that cluster I quoted you the stats on earlier. Every single second a read is failing because we query it all the time. And every single query that comes into Tempo results in thousands and thousands of requests to the actual object storage. And so we talked about P99, right? So 99.99% of the time, you're going to get a successful return. But when you execute 3,000 queries against object storage to get a piece of data back, to get a trace back, one of those is going to fail by definition of the SLO. You have to write code as if you're always failing. So it's an important part of using object storage, just always being ready for it. Request hedging is also a tool we've used a lot, and I'll go into that detail of that a little bit in a second. And we also even have, we haven't turned this on, but we have a feature, which I think is kind of funny, where we just allow some blocks to fail and still 200 the request. So at times we've had as many as 20,000 blocks in our backend that we have to search for these traces. If 2 of those blocks fail, should you fail the request? Or you should just return 200 and whatever you happen to get on, the rest of the data. So it's kind of a fun, there's some interesting like failure modes in Tempo that are between success, complete 100% success, and failure. And we have some like ability to tolerate some amount of failure on our backend built in. This is also failed writes. So we had this week where we were failing writes all the time for hours. If you look at that horizontal axis, you'll see this is an entire week of data. So for hours at a time, we were failing to write to GCS. No idea why. We filed a support ticket. We're talking to them. Eventually the answer comes back, we're with an SLO, deal with it. You have to be this. If you're going to write code against object storage, it will fail. These are our SLOs. Write code as if it's going to fail. So that was an important lesson for us. And we had a lot of good queuing logic. Actually, I was very happy with Tempo through this period because everything just worked. We continued to queue things on disk. We continued to retry that queue until GCS started working again, and we really didn't have any lost data. So at some point, you're pushing on your cloud provider. Why is this stuff failing? What's going on? They're going to tell you they're with an SLO, and that's it. And you have to be able to write code that's handling failures all the time if you're going to use object storage. Request hedging, I love request hedging. We've used it repeatedly in Tempo. It's kind of a broken trick, and it's a lot of fun. It's the simplest idea ever, and it just lowers your latencies considerably. So at its simplest, hedging requests is just every single request to a backend, issuing it twice and waiting for the first one that returns wins and ignoring the return for the second one, basically. We don't quite use it like that because that would double our access costs. So we have a timeout, and this is a common approach as well. So we issue one request, 400 milliseconds later, if that request hasn't returned, we issue a second request. Now 400 milliseconds was chosen because that's our P99 of GCS. And so we only repeat 1% of all of our requests. It almost has zero impact on the use of object storage. And this idea came from a paper that's kind of linked in our slide here, which is a very popular paper. I wish I had the title there. It's called The Tail at Scale. I recommend looking it up if you build anything like this ever. But they talk about if you are building a system that executes 10,000 requests against some other backend, how to handle that, because some percentage of those will always fail. And the hedged request idea is from there. So we set this hedging timeout of 400 milliseconds. We repeat the request. If it doesn't come back because it just happens to be slow, we don't even care why. There's no reason to diagnose this. It just happens to be slow, so ask again. And the first one of the two that comes back is the data we use. This is our latencies when we implemented this. So we had this P99 that was hovering in the single digit seconds, and it just flattened it instantly. And it created a whole lot more stability in our latencies all of a sudden, where before they'd fluctuate a lot. P99, P90, P50 all came down a lot, or some, P99 especially, because we just reduced variance in our query path by adding hedging. Organization, the way we organize data is also very important when you use object storage. So part of the challenge here is you are using 3 different backends, really. We use 3. There's other kinds of object storage. We're using GCS, S3, and it's called Azure Blob Storage, Frederic. But we're using all 3 of these. We have support for all, and in Tempo, there's this clever little shim. It's an interface, right? And we pretend that the interface makes all our problems go away and all the object storage can be treated the same. And that's just not true. They all behave slightly different. There's subtle differences in their consistency model. In fact, Azure Blob Storage is kind of currently a pain in my ass because it is just its consistency model seems to be very different than S3 and GCS, and I'm struggling to work with it. There's quotas, there's limits, there's just all of these details that come with learning each of the three. And so while we pretend that we have this very common model that we can treat all of our backends with, it's just kind of not true. It's a very leaky interface or a very leaky abstraction. And so we often are thinking about this backend. So that's kind of one of the challenges in data organization. As a result, we made very simple design choices. Almost all of our objects are immutable. There's only one that we change, that we rewrite, but everything else we write once and we never change it. So every time any pod, any of our different processes read it, it can have the expectation that everybody else is seeing the exact same thing on the back end. And we also built we also built Tempo around the idea of polling. Like S3 supports events. You can like get an event, announced event when something changes in your backend, but we didn't want to use any of that. Let's keep it as simple as possible. The different components are going to poll the backend to determine their state. This does add some complexity because different pods can see different states of the backend, but it works out, I think, better in the long term. It's a simpler method of interacting with your backend. And then the last thing I want to talk about is a very important design decision in Tempo, which really helps with our parallelization and is very important if you're storing terabytes and terabytes of data in object storage and you need to access this. And it comes with a couple of names like cache invariant, cache agnostic, or cache oblivious. If you look up some of these, you'll stumble upon some of these algorithms. It's a very important class of algorithms when you're dealing with this much data. And to start the discussion, I asked the question, how do you sort 10 objects, right? And the answer is nobody cares, just it's all in memory. Call your stupid Python sort function and pass the slice in or the array or whatever Python uses list. And it's sorted and you're done. It's easy. But how do you sort an enormous number of objects? How do you sort a number of objects you can't store in memory? Or you can't even store on the local disk? How do you go about attacking these enormous data sets? And the answer is through this class of algorithms called cache oblivious algorithms. And these algorithms are for sorting and matrix multiplication and all kinds of different algorithms where the whole data set cannot be held in memory at once. And we write an algorithm that just works on a small piece at a time. So no matter how big our local cache is, no matter how much data we can work on at once, we'll eventually solve the problem. So we built all of Tempo around this idea, where each individual request is blown out into thousands and thousands of sub-requests, which are all executed in parallel. And each one has a small amount of work to do. There's no single point of, I have to pull in this 2 GB file. There's no giant index that needs to be pulled in, but each group, each parallel process, or each parallel job can access a very small amount of data and do its work. And we can use configuration options to make that amount of data bigger or larger, depending on kind of how much we want each parallel job to do. I don't want to get on into all the details here. I'm kind of out of time, I think, but both the trace by ID and search path are built around this idea where we can make our jobs as small as possible and blow it out as wide as possible in parallel. So yep, thank you all for listening, and thanks to Natalie and Frederic as well. I really enjoyed their talks. But please join us over at Grafana, talk about Tempo and some of the Slack channel or on the GitHub repo or in our community forums. And with that, I'll give it back to Mike.
Awesome, Joe, thank you so much. This was great, very comprehensive, and you undersold the amount of detail you actually put in there. All three of you actually, tremendous amount of detail. Quick side note, I was giggling when you were talking about a certain cloud vendor's blob storage. When I asked them if they used the S3 standard, they told me it was a trademark, not a standard. So thought that was a funny little quip. All right, one more time to just plug Acuity for sponsoring this. We want to thank them again before we get into the panel discussion. Every third newsletter, register, gets a swag bag from Acuity. Again, awesome icons and branding and t-shirts, or whether there's t-shirts in there or not, I don't know, but even if it's just a sticker, it's awesome. So get after it. All right, so from a panel discussion, Joe, we kind of in the pregame, we had talked about how you might have some questions that you think would be relative to the cloud native community for your peers who presented with you. So do you want to start with some of that?
Sure. I'll actually start with a question for Natalie. I think eBPF is a really cool technology, and I mucked with it a while back. I was using dynamic or U-probes or dynamic, doing dynamic tracing using U-probes. That's what it's called. My bad. You know all this, I'm sure. But my challenge was I was trying to do it on .NET Core, which is a managed language, and it was quite difficult. I actually just happened to stumble upon a lot of different really niche resources to get me to the point where I could do this. So my question for that particular technology, what I think is mind-blowingly cool, is what languages and frameworks are just dead simple? What requires some work? Are there any that are impossible? Like, are there any that we just can't do dynamic tracing on?
Yeah, it's a great question. So just to clarify to the audience, eBPF has multiple kinds of probes, and the main ones you often hear about are K probes, which are kernel probes on things like syscalls, and U probes, which are actually on code in the user space. So if I write an application, I can use a U probe to trace what's going on when one of the functions that I wrote is called. So basically what you're asking is, if you want to do these U probes, like what languages does it work well for? So in my experience, it definitely works the best for things like Rust, Go, C++, because the story around the symbols is, like fairly straightforward. We actually also see some like weird compatibility sometimes with Node, because it calls out to C so much that you can sometimes see what's happening there, even though it's not the JS code itself necessarily. I can't necessarily speak to like the future of like how that will be for something like Python or whatnot, but I think that it's something that the BPF community is aware of and working on. And my hope would be that, even if you can't do it exactly the same way with the symbol, because it's not the same type of language, there would be some other thing that you can trace. Something is eventually happening to call that code that maybe you could stick stuff in. But today, to answer your question, it's the compiled languages that it is just dead simple for.
Thank you. Yeah, that's really cool. I just love that technology. Well, the first time I attached a uprobe to a random function in my code with no instrumentation and just saw every single call, was able to dump the arguments and the return value. It was really neat. It was just a new way to look at a program for sure.
Yeah, we have to deal with this problem a lot with continuous profiling as well. And it's with profiling, this is there's definitely a lot of prior art because there's the entire perf subsystem in Linux. So in particular, because you mentioned .NET, .NET is a JITted language. So there are some benefits to that, because with a just-in-time compiled language, there is still machine code that is being executed at the end. And so that's kind of what Natalie was saying, like machine executable code tends to be much easier to deal with because we don't need to understand the internals of the virtual machine. We are actually working on actual support for Python, Ruby, Java, and all of these. But these do require specific integrations, and they require knowledge about those virtual machines. Because we mentioned Python earlier, Python internally in its virtual machine essentially builds a virtual CPU. And so it also builds stack frames just like the operating system does. And you just, quoting the right? You just need to read the memory from the Python interpreter to find the correct location where that's being held, and then you can symbolize those stack traces in a similar way. I don't know if that will work with all sorts of probes, but it certainly does work with the profiling case. But yeah, it's a lot more work for non-compiled languages, and actually even compiled languages can sometimes be a pain when there are compilers have been around for decades, and there are very evil compiler optimizations that make these things really hard as well. In particular, things like skipping frame pointers. If people are not aware, essentially frame pointers are kind of a preamble at the beginning of the assembly code of your function that kind of says where the previous function left off. And so when we have these, it's very easy to just walk this linked list to create the stack. But if we don't have them, I won't get into it, but it's very complicated to reconstruct the stack then.
Yeah, it can definitely be challenging. You're making me think of some struggles I had actually a couple days ago with functions getting inlined, and I'm like, oh my god, now I can't see anything. Or which shared library is this function in? Oh my god, there are 20 of these shared libraries. I have to go through all of them and figure out which one has the actual function definition. So there's plenty of work to be done.
It's a great start to the discussion. Thank you so much, Joe, for kicking it off. I know that you have a couple more questions. I just wanted to remind people that are on the call that you can pump any questions into the Q&A, and we will be happy to present them to our distinguished presenters. I know that I had some cardinality ones kind of staged and a side conversation with my esteemed colleague, Ryan at BlackRock. I'm going to let him ask it. So Ryan, you have a question for the group?
Yeah, one thing we struggle with, specifically at BlackRock is cardinality of all our metrics. And, we add all these metric providers in our clusters. You start getting hundreds and hundreds to thousands of clusters, and you start having some insane cardinality. So just kind of a question to the group, as you're adding more metric providers, how do you manage your cardinality and try to reduce all the different sources of metrics, I guess?
Noise. How do you distill it down to the appropriate amount of noise?
Yes, actionable noise.
Actionable noise, that's probably better said.
So I think there are some tools to do this, but I want to highlight something that Frederic talked about a little bit in this conversation, because it's also a path we're looking at in Tempo, which is to stop caring about cardinality and start storing in column or data stores. This kind of data store is a lot more efficient at storing extremely high cardinality data because it doesn't attempt to reduce the cardinality. It just stores every column independently, which allows for much faster querying. In fact, Frederic is working with some of the same people we are, because we are also looking at building a column or data store in Go using Parquet on object storage. So we have different goals here. He's looking at continuous profiling while we're looking at tracing. But I think some of the members of my team, as well as Frederic himself, are kind of working together on improving some of the tooling here. Now, in terms of a traditional storage, I don't know. I bet Frederic might be able to talk a bit more about how to do that in Prometheus, about how to reduce cardinality. But it is a problem in those kind of databases. I think the thing where we misframe the question is the point of having these cardinality limits is the insane speed with which you can ask Prometheus for things, and you can ask Thanos and Cortex for things. Like with a column or data store, when you try to give up these restrictions on cardinality, you're just never going to hit the same speeds as a database that has restricted its cardinality and can access that. But I'll let the expert answer a little bit more about some options there.
I do want to also note that even if we use columnar stores, we're still, the more data we have, the more we need to store, the more it's going to cost, right? We might be able to reduce the cost of cardinality by a significant margin, but no matter what we do, if we have more data, we're going to pay in one way or another. And like Joe was saying already, that like the fundamental architecture might mean that we pay by having less fast queries, but fundamentally, even on a just talking about the storage, more data means more storage. That's never going to change. Again, we can make it cheaper by having great compression and things like that, but fundamentally, more data means higher cost. But
Frederic, on that point, it's a large financial institution, right? We look at data, especially within our portfolio management space, as currency, right? So what is the total cost of ownership of that currency and the return on investment we get from the amount of data we store, right? The more data we can, especially within the portfolio management space, the better investment decisions and modeling we can do forward projecting on top of it, right? So there's always that constant balance of cost total cost of ownership, and the return on investment. And Frederic, while we still have your mic hot, there is a question in the room for you. So Frederic, you mentioned tracing profilers have large overhead, true. But what about tracing profiling built on top of eBPF? And what are your thoughts there? I think you touched on this in some of your presentation, but to recap, if you already stated it.
Yeah, so Natalie was kind of talking about this, and we don't really have like distributed tracing with like very high quality that we can produce from eBPF today. And I think the kind of fundamental difference with distributed tracing versus profiling is that distributed tracing will always require human interaction and will always require the human to do the instrumentation, and that's a good thing. While some like often it's seen as a negative, right? That's why distributed tracing data is so high quality. People actually think about it, right? Whereas with profiling data, it is actually reflecting the way that the machine is executing the code, right? And that's never going to be the same with manual instrumentation.
Awesome. I've got just from a developer's perspective, after KubeCon this past year, I'm not sure what the thematic layout is going to be for this year. I think I have some ideas, but coming out of last year's KubeCon, there was a lot of talk around, right? There is increased adoption. There's increased adoption in the spaces where adoption wasn't as high in the containers and Kubernetes space, especially like companies like my own, right? Big financial institutions, highly regulated institutions. Developer agency and developer productivity velocity became very, very high, or very, very important kind of messages or undertones in KubeCon this past October in LA. How, Natalie, to you first, how can Pixie, the open source project Pixie, help with that developer agency getting quick access to this level of observability, and then Grafana Labs and Parka / Polar Signals, you guys chime in after.
Yeah, so I think that there's a lot to say there, but I'll focus on like one particular answer to that. So Pixie was made for developers, and it was made with the belief that debugging production is so much harder than debugging your local dev environment. It's not even funny. Yet at the end of the day, when there's a production issue, the developers eventually have to get involved to figure out what's going on. And they are like thrown in the deep end because all the stuff that they have locally just does not exist in production a lot of the time. And so when I was part of those types of incidents, it was very painful, very time-sucking, totally throws off whatever you were doing, kills productivity. So by bringing tools that mirror the information that you have in your local environment, it should really, really, really reduce the amount of time that you spend trying to figure out what the heck is going on in production. So I think that that's one answer to your question. And I think that, you know, BPF is a huge part of that just because of the richness of the visibility that it provides. And what Pixie provides on top of that is scriptability, so that I can ask very customized, targeted questions. I don't just get stuck at a single line chart and like, that's the end of it. And so I will often be coding up scripts to answer like very specific incident related things in order to understand what's going on. And so for me, as someone who debugs our systems, that helps me a lot with my productivity.
Awesome.
This is funny. I want to write on that a little bit. But this is about 5 years ago, before some of these things, before continuous profiling, as far as I know, existed. But we had this issue in production, this exact same thing that Natalie's talking about. It only happened in production. Nobody could reproduce it locally, but we had a service that stuttered occasionally. Nobody understood why. And so I wrote a script that took a profile every 5 seconds and just dumped it to disk and just let them for days. And eventually it just happened to catch the error, and we were able to use it to determine where it was in the stack trace at that time. And it was extremely powerful, but it took days of my time to go write this special bash script and debug it and set it up and get it in the right spot. And then to see the thing actually happen, you know, it was such a pain in the butt. I can't tell you how excited I would have been to spin up like a continuous profiling application and just point it at the thing and to just wait for that to catch it. Or, some of what Natalie's talked about with the BPF technologies. Absolutely, like interacting with production is sometimes extremely difficult. And I love that these tools are kind of exposing that ability because there are just some bugs that only happen in production. And there are some bugs that you have to have the visibility there. And these low-level tools to give people some of the stuff they're used to in their local dev setups is really cool.
Yeah, it's great. Like mean time to resolution. It's from an SRE perspective, it speeds up all of those things. And to Natalie, to your point, developers, whether they're phoned at night, on the weekend, or just in time during the day, you are literally thrown on the deep end, and everybody's looking at you with a large set of optics on, saying, why? Tell me why. Help me figure out why. And the better, more sophisticated that tooling is, and the deeper you can go, faster mean time to resolution, right? That's what we're all looking for. You want to get off that event call as quick as possible. All right, Frederic, anything to add there?
I think it's just funny how similar my story is to Joe's, because what essentially made me make all of this my full-time job is that I was working on these super performance sensitive pieces of software like Prometheus and Kubernetes, and I had all of this wonderful observability tooling, right, like Prometheus, logging and tracing with Jaeger, but I found myself profiling my applications all the time, and I was like, this doesn't make any sense. Like, observability isn't about a single source of data or a restricted source of data. It's understanding all aspects or any aspect of our running systems, right? And so that was essentially what inspired me to, as I said, make this my full-time job, because I'm convinced that, and continuous profiling is really just one of those examples, I think, and which is why I think what the Pixie folks are doing is really cool. I think there's so much more data out there that does exactly what I just said, which is help us understand various aspects and facets of our running applications.
It's a great point. I want to just dive in on really quickly with everybody, because the 2021 after action report, the survey the CNCF does, 63% of companies that are adopting more cloud native microservice, single responsibility, pick the buzzy word service term you want to use for cloud native services, the more and more their adoption grows, the higher they're seeing where they're cloud vendor first, right? Where their cloud costs are also increasing. So 63% of the companies that have adopted more cloud native practices and cloud providers, which help provide better landing zones for more cloud native applications in most cases, they see that cost going up. So from an open source perspective, I run our internal OSPO at BlackRock. The need for more people in the open source community to come interact and engage with you all, Joe, Natalie, Frederic, in the community, and help solve, especially around this, how we can leverage object storage, a cheaper data store at still and still meet the scale and velocity and business requirements we have across our relative businesses, is really important right now. And I think going forward, because there's a great Forbes article called "The Cloud Candy Shop is Not an All-You-Can-Eat Buffet." And I think that what you all highlighted today from a data storage perspective, it's not cheap. And then even if you use the cheap stuff, it can be simpler. But you talked about multi-threading. If one thread's 50 megabytes a second, right, Joe? You need to do this thing in parallel, right? And then there can be some data loss there, and you need to have your developers both understand what they're doing and the ability to tile that together, given whether it's a vendor SLA or the requirements of the platform you're using. Like, as an engineer, I love being a problem solver. These are all really interesting problems to me. I hope they're equally interesting to everybody else on the call. And the open source is an engaging community. Please, reach out, talk to these folks, and figure out how we can help drive this forward, because I think it's gonna yield some level of cost savings for everybody that's rapidly going to the cloud or rapidly adopting cloud native and editorializing over there. Any additional questions, Joe, you had, Natalie, Frederic, anything you wanted to ask your peers? We're getting close to time, and I wanted to make sure that we could open the floor for any open questions that people didn't type in. All right.
Going once, going twice.
Any questions from the audience?
Everybody, so I've unmuted if you want to unmute yourself, or enable you to talk if you'd like to unmute yourself and ask a question. Okay, Mike, let's wrap it up.
I want to thank our presenters. Thank you so much. Amazing content, amazing presentations, great discussion. Ryan, thank you so much for the short notice join and asking good questions. Everybody can go to the Cloud Native at Scale meetup, look at future events. I think Josh is potentially sharing one here. I want to give one final thank you to Acuity for being the sponsor, and we really appreciate their support. And thanks again for everybody taking the time in the middle of your day or beginning or end to join us, and enjoy the rest of it. Thanks so much. Josh, to you.
Yeah, no, I think you covered everything. So this is our next event right here. It's confirmed, scheduled. Some people come through the Eventbrite platform, so I invite you to join our community if you're not already. And we focus on mostly the CNCF Foundation projects. So about 95% is focused on that. So I just want to thank our speakers. You guys are true entrepreneurs, true innovators, working on open source projects. And it's really just phenomenal, the work that you do. And it's an honor to have all of you. So great. Thank you so much. And we'll be in touch, and take care, everybody. Thanks, Mike. Appreciate it.
You're welcome. Here.
Okay,
Have a good
take
day.
care. Bye.